Kia ora koutou, this is video 2 from yesterday's extension class on level 3 differentiation, and this video finally gets us into implicit differentiation. So I'm starting slightly backwards. I'm starting with what was an excellence question from last year's exam. In some ways it's a really, really easy implicit question, and then the next thing that I'm going to do is from a book that I won't mention. I've just grabbed some practice questions at doing lots of implicit differentiation. So the first one is, a classic NCEA nice applications problem. You've got to do some differentiation, but it's got a purpose, right? We've got a curve that looks like this, and it's got a tangent of gradient 1 at point P, right? And so we've got to figure out, obviously, where is point P, because we're told that this tangent line intersects the x and the y axes at points R and S respectively. So looking at this question, you can do this in the exam, right? Get your ruler or your snapper card or whatever it is. Actually, it probably can't be a snapper card in the exam, it probably has to be a ruler. And just let's draw that tangent line in. What I'm looking for is the points R and S. So R is where it intersects the x-axis, so R will be here, and S is where it intersects the y-axis, which will be here. And we have to show that that length RS is 7 root 2. I really liked this question. And again, I think if you can do implicit, it's very, very easy. Then the next ones we've got are a bunch of different things to differentiate. And you can see, as I mentioned in class yesterday, the x's and y's mixed up is where we usually really have to use implicit differentiation. So the instruction here is just to differentiate each of these things with respect to x. So all I'm trying to do is d blah, 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 by dx. So these questions look a little bit different than the ones we were looking at yesterday in class, where we had a relationship. So we were given a curve, right? So x squared plus y squared equals 4, and we differentiated both sides of that with respect to x. And here, we're just differentiating the expression with respect to x. Anyway, I'll do the NCEA question first. And again, I'm pretty sure that I did this at the time of last year's exam, so there might be another video already done. Okay, let's get rid of the line for now and do the differentiation. So over here, we've got y minus 5 squared is equal to 16 times x minus 2. So the logic of implicit goes like this. I know that this is equal to this everywhere if I'm on the curve. And that means that if I change something on one side, that has to equal the change on the other side. So what I'm doing when I do implicit differentiation is I'm saying, let's find this d blah, blah, blah by dx. So when there's a little change in x, what happens to y minus 5 squared? And that will be the same as when there's a little change in x, what happens to 16 times x minus 2. Right, so when we differentiate this, we can't directly differentiate this with respect to x, but we can differentiate it with respect to y. So we're going to use the chain rule, and we'll have this. So very slowly working this through. You don't need to write this line in, but this is what we're doing. We're saying we'll differentiate this thing with respect to y, because we can, and then we'll use the chain rule to get the change with respect to x. And then on this side, when we differentiate this with respect to x, this is very easy. It's just 16 because this expands to give me 16x minus 32. Okay, so all we've got left to do is to do the differentiation on the left-hand side. By the chain rule, I get 2 times y minus 5. The derivative of the inside function here is just 1. So I've got 2 times y minus 5 dy by dx is equal to 16. That gives me, rearranging, dy by dx is equal to 8 over y minus 5. Now we were told in the question that we're interested in the point P, where the gradient of the tangent, where's my question gone? Hang on. Yeah, the tangent has gradient 1 at point P, right? So far we've worked out that dy by dx is equal to 8 divided by y minus 5. And we're now going to figure out where is that going to happen, or where is the gradient going to be 1. So we get y minus 5 equals 8, y is equal to 13. So we know that that value there is 13, and now we have to work out using this, what's my x value? So substituting in 13, gives me 13 minus 5 squared is equal to 16 times x minus 2. 13 minus 5 is 8, 8 squared is 64, so we have 64 divided by 16 is equal to x minus 2. That's 4, 4 plus 2 is 6, so we get 6 is equal to x. So that's telling me that that point there is 6. Now we'll put that tangent line back on. Try and make it roughly accurate. We want to find the equation of the tangent to the curve, and we know a point, and the point is 6, 13. So we can either use y equals mx plus c. I'm going to do this in two ways. In both cases, I'm going to use the point 6 and 13, and we know that m is equal to 1. So we have y is equal to x plus c. Substituting in, we get 13 is equal to 6 plus c. c is equal to 7. That gives me y is equal to x plus 7 as my tangent line. Okay, so from here, it's pretty easy. I can either use my original graph, or I can just do a little sketch here. Just make my pen a wee bit thinner. So I'm doing this slowly because I really want all of you doing nice sketches to help you solve problems like this. This is point, which point was this? This is S, and we know that S is equal to 0, 7 because it's the y-intercept. And this is point R. So R is where y is equal to 0. So y is equal to x plus 7, so x is equal to negative 7. So this has coordinates negative 7, 0. And we can use Pythagoras now to figure out the length of SR. So SR is equal to the square root of this squared plus this squared, which is equal to, from here, I'll go really slowly. This is equal to the square root of 98, which is equal to 2 times 49. I really don't know why I bothered to do that step. Here we go. And now we get this is equal to root 2 times 7, which I can write as 7 times root 2. So there you go. I think that if you know how to do implicit, that conceptually that's a very easy excellence question. The way that I saw some of you doing it, which is good if you don't like implicit, and I'll just get the question to come back up on the screen somehow, is that you can, in this case, make y the subject, right? You don't have to work with implicit. Where I'd like most people who are coming to the Saturday classes to get to, though, is that you see implicit as a really easy and useful technique to use, not as something that's scary at all. But you do have to be confident with the chain rule to make it work, right? Like here, you have to recognize that it's going to be 2 times y minus 5 times dy by dx. So that might be a place where some of you need to practice, is not on implicit, but on the chain rule. So doing it the other way, we can do this. We can go y minus 5 squared is equal to 16 times x minus 2, which I'll write as 16x minus 32. Taking square roots of both sides, I get y minus 5 is equal to plus or minus the square root of this. And then we have to recognize that point P is on the top bit of that, so we want the plus square root bit. And then we get y is equal to 5 plus that. And you can go from there, right? So now you can get dy by dx. And of course, you'll get the same point, which is 613. But differentiating this is definitely more painful than doing implicit on this. Okay, I've got 6 minutes left. So I'm going to start on some of these implicit differentiation questions. So the first one, dy to the power of 4 by dx is just equal to this. We can't differentiate y to the power of 4 with respect to x, but we can differentiate it directly with respect to y, and then we'll use the chain rule. So my answer here is going to be 4y cubed times dy by dx. And that pattern is going to work for quite a few of these ones. So for this one, where I don't have any mixed up terms, number 2, we get this. We'll just do this term by term. So the first term goes to 2x. The second one will be 3y squared times dy by dx. And when I change x by a tiny bit, nothing happens to -5, so that's just 0. So that's the end of that one. Right, the next one is the first one where we have to use the product rule. So we want to differentiate xy plus x plus y with respect to x. Treat this as u times v. Right, so this is u times v. So the first bit is x here, and then when I differentiate y with respect to x, it's going to be dy by dx. And now I have to go the other way around. So this is u v dash, and now we're going to have u dash, which is 1 times v. So we've got u dash times v, 1 times y. Now we're on to the next term, plus 1. And when I differentiate y, I get dy by dx. All right, so that's an adequate answer. It's a pretty ugly answer, so I'm going to do a little bit of cleanup because I can't help it. So I get, let's see, x dy by dx plus y plus 1 plus dy by dx. Now that's fine. Probably if I were using that in a problem, what I'd want to do is collect up and factorize out that dy by dx. So I'm going to do that here just to give you practice at it. So we've got dy by dx into x plus 1, covers off this term and this term, plus y plus 1. So I would tick that one. I would also like that solution there. Okay, what's the next question? Right, now we've got some trig. Oh, we've got a trig and then an exponential, and then I'll probably stop there for this video. So here we've got cosine of y. So y, cosine of y, and we want to differentiate this with respect to x. So we're going to do the chain rule on this. When I differentiate cosine of something, I get negative sine of y, and I have to differentiate the inside function with respect to x, which is dy by dx. So that's my answer there. The next question was e to the y plus 2. We have to differentiate this with respect to x. So again, we're going to have the chain rule on this. So I'm going to differentiate this with respect to y and then use the chain rule to differentiate the whole thing with respect to x. When I differentiate this with respect to y, I get e to the y plus 2. I check my inside function, but its derivative is just 1, so I can keep going. So my answer here is this, e to the y plus 2 times dy by dx. I've got a few left to do, but I think 13 minutes is long enough, so I'm going to stop there and I'll keep on going in video 3. Thanks for watching.